Cambridge International GCSE Chemistry, Paper 2, Tip number 6, Equilibria. Paper 2 questions have focused on the themes of reversibility, equilibrium descriptors, the effect of condition changes, that is Le Chatelier's principle, the Haber process and the details of the contact process. Questions usually appear in the range questions 13 to question 18. There are 2 reversible reactions you are expected to recall the laboratory details of. The first one is the reaction of anhydrous cobalt chloride, which is blue, with water to form hydrated cobalt chloride, which is pink. So you have probably met cobalt chloride as a cobalt chloride paper. So cobalt chloride paper and water turns pink. Now, this is reversible. You may have seen it demonstrated with a hairdryer. If you warm the hydrated cobalt chloride or the damp cobalt chloride paper, it will turn back to blue. The second reversible reaction you are expected to know the details of is that of anhydrous copper sulfate, which is white, with water to make hydrated copper sulfate, which is blue. You are expected also to recall or recognize the correct formula. So copper sulfate, CuSO4, that's anhydrous. The hydrated, CuSO4.5H2O. This is the hydrated salt. If you've done this in the laboratory, you'll find, of course, that this reaction is exothermic. This test tube is very hot. So the forward reaction, left to right, from anhydrous to hydrated, is exothermic. It gives out heat. That means, of course, that the reverse reaction must be endothermic. So to achieve that, to turn blue into white, we apply heat with a Bunsen burner. You may have seen that demonstrated or carried it out. So blue hydrated copper sulfate, if heated, goes back to white. So those are the 2 reversible reactions you are expected to recall. So we have reversible reactions. So what is therefore meant by equilibrium? Well, when reversible reactions occur in apparatus which prevents the escape of any particles, which has a technical term, a closed system. That is, the reactants turn into products, products turn into reactants, nothing escapes from that system. Equilibrium is reached at a point when the rate of the forward reaction equals the rate of the reverse. So if we start off with looking at this graph here, rate of reaction against time. So we've got a high rate of reaction for the forward reaction. The reverse reaction is 0. There isn't any product to reverse. As time goes on, the rate of the forward reaction decreases and the rate of the reverse reaction increases until they reach the same rate. You may be expected to interpret this graph. At equilibrium, excuse me, the concentration of reactants and products remain constant. So 3 descriptors, closed system, rate of forward equals rate of reverse. The concentration of reactants and products remain constant. Often a multiple choice question. Let's have a look at the effect of concentration change on what's called the position of equilibrium. And here is a statement of Le Chatelier's principle. The position of an equilibrium will move to oppose a change in concentration or amount. So if we look at an equilibrium of P, Q and R as reactants, reversibly forming S and T, if the concentration of P is increased, the equilibrium will move to oppose that change. So the equilibrium moves to the right to decrease the amount of P. So here's P on the left. If we increase the amount of P, the equilibrium moves to the right, forming S and T, and therefore decreasing the amount of P. Q and R must also therefore decrease. So if P reacts to form S and T, then it must involve Q and R also being used up. So Q and R also decreases. S and T must increase. If the concentration of S is increased, so we're going to increase the concentration of S, the equilibrium will move to oppose the change. So the equilibrium moves to the left to decrease the amount of S. Well, if we're decreasing the amount of S by reacting it with T to make P, Q, and R, then it follows that T also decreases and P, Q, and R therefore increase either in concentration or amount. So let's look at the effect of pressure change on the position of equilibrium. Again, here's a statement of Le Chatelier. The position of gaseous equilibrium will move to oppose a change in pressure. So let's look at a gaseous equilibrium. N2O4 forms 2 molecules of NO2, nitrogen dioxide or nitrogen 4 oxide. 1 mole on the left-hand side, 2 moles of gas on the right. 2 moles of gas exerts a higher pressure than 1 mole of gas by collision with the container wall. So the right-hand side is the higher pressure side. If the pressure is decreased, the equilibrium moves to increase the pressure. How can it do that? Well, by turning N2O4 into 2 NO2s. So let's imagine we start with 8 molecules, a mixture at equilibrium. We've got 5 N2O4 and 3 NO2. If we decrease the pressure, the equilibrium will move to the right to convert N2O4 into 2 NO2s. So if we have a new equilibrium position following the decrease in pressure, we've only got 2 N2O4s. That means we now have 9 NO2s. So we've got a grand total of 11 molecules on the right-hand side, and that therefore will increase the pressure. So we say the position of equilibrium has moved from the left to the right. That is, on the left, we had 5 N2O4 and 3 NO2, and on the right, we have 2 N2O4 and 9 NO2. So the position of equilibrium has moved to the right. That increases the moles of gas, and therefore, another term to take note of, the yield of NO2, the relative numbers of moles of NO2 compared to N2O4. So we say there's been an increase in the yield of NO2. Let's look at temperature change effects. Here's Le Chatelier. The equilibrium will move to oppose a change in temperature. Consider hydrogen and iodine making 2 moles of hydrogen iodide. Delta H for that equilibrium is plus 26.5, which means it is endothermic in the forward direction. So that means the forward change produces a drop, a decrease in temperature of the surroundings. So if a temperature increase is imposed, that will move the equilibrium in the endothermic direction. So a temperature increase is imposed, the equilibrium will move to oppose it by moving in the endothermic direction, that is trying to produce a decrease in that temperature rise. Now, if the forward reaction is endothermic, the reverse reaction must be exothermic. So from hydrogen iodide to hydrogen and iodine, must be exothermic, and that will produce a rise in temperature. So if a temperature decrease is imposed, then the equilibrium will move in the exothermic direction to attempt to increase the temperature. Please note, a catalyst has no effect on the position of equilibrium. It simply increases the rate of the forward and reverse reactions to the same extent, and therefore the position of equilibrium is not changed by the presence of a catalyst, although the rate at which equilibrium is reached is increased. There are two industrial processes which employ equilibria you are expected to know the details of. The first one is the Haber process. This is a reaction between nitrogen, 3 hydrogens to form 2 moles of ammonia. Delta H is negative for the forward reaction, so that is exothermic in the forward direction. The forward change produces a rise in temperature. So how could we increase the yield of ammonia, the relative amounts of ammonia compared to nitrogen and hydrogen? Well, by having a high pressure, 200 atmospheres is employed. There are 4 moles of gas on the left, 2 moles of gas on the right. Therefore, the right-hand side is the lower pressure side. So high pressure will push the equilibrium or the position of equilibrium to the right to increase the yield of ammonia. A low temperature would give a higher yield of ammonia because the forward reaction is exothermic. But please note, the industrial temperature used is a compromise at around 450 degrees Celsius, because if we did use a low temperature, then the rate of reaction would be very slow. So to have a decent rate of reaction and yet a decent yield of ammonia, 450 is employed. You are expected to recall those two conditions, often just factually. The catalyst for the Haber process increases the rate at which equilibrium is reached, but has no effect on the yield of ammonia. Again, often asked in a tabulated multiple choice. The identity of the catalyst also questioned. It's iron. The second industrial process, the contact process, is part of the manufacture of sulfuric acid. But the contact process itself refers to this equilibrium, sulfur dioxide and oxygen forming sulfur trioxide. The forward reaction is exothermic. Multiple choices focus on a recall of the conditions: 2 atmospheres pressure, 450 Celsius. Again, for the same reasons as the Haber process, this is a compromise between rate and yield. So the 450 temperature and 2 atmospheres pressure needs to be factually recalled, as does the identity of the catalyst, vanadium 5 oxide, V2O5. Vanadium, a transition metal. Obviously, you need to practice some past paper 2 questions. You'll find these in the range question 13 to question 18 on equilibria. If you don't have past paper 2 copies, I recommend Physics and Maths Tutor. It's a website that has access to more or less unlimited supplies of CIE, GCSE chemistry papers. If you found today's lesson helpful, please recommend it to a friend. Please like, and if you don't mind, it's not inconvenient, please subscribe.